Hey students, I welcome you all for the lecture videos on digital signal processing. Today we are solving problems on bilinear transformation, that is design of digital filter using bilinear transformation. Let us consider the problem. It goes like this. Design and realize a digital low pass filter using bilinear transformation method to meet the following specifications: monotonic stop band and pass band, minus 3 dB cutoff at 0.5 pi radians, minus 15 dB attenuation at 0.75 pi radians. Assume t is equal to 1 second. Let us consider the solution. We are doing the design of digital filter. We are designing the digital filter. When we want to design any digital filter, we should do pre-warping of frequencies, especially in case of bilinear transformation method. Okay, so gains are constant whether it is analog filter or digital filter. The gains remain same, so therefore I will take Kp pass band gain, which is equal to minus 3 dB, stop band gain, which is equal to minus 15 dB. Okay, now I am doing the frequencies. Now whatever the frequency it is given, it is digital frequency, so therefore Wp is equal to 0.5 pi radian per second and Ws is equal to 0.75 pi radian per second. This is the frequency, digital frequency. Now we cannot take this digital frequency directly for design of any analog filter, so therefore we can do the pre-warping. So what is the formula for pre-warping? It is given by omega 1. So omega 1 star, it is nothing but we are doing the conversion. Okay, so conversion from digital frequency to analog frequency is called pre-warping. It is given by 2 by t into tan of W1 by 2 or Wp by 2. So what is the value of that? T value is 1. So tan of, what is the value of W1? It is 0.5 pi by 2 radian per second. So if you simplify, you will get omega 1 star or omega p star is equal to 2 radian per second. Similarly, we can calculate omega 2 star or omega s star, which is equal to 2 by t into tan of W2 by 2. If you do that, 2 by 1 into tan of 0.75 pi by 2. So if you simplify, you will get omega 2 star is equal to 4.828 radian per second. These are the corresponding analog frequencies. Now we know what is Kp, what is Ks, what is omega 1 star and omega 2 star. Now we can design the normal analog filter, then we can go with the digital filter by using bilinear transformation using the corresponding transformation formula. Now I am going with the step 1. Step 1 is to draw the magnitude response characteristics of low pass filter. So we will have the Kp, we will have Ks, we will have omega p, we will have omega s star. Okay, Kp, Ks, it remains same. This is h of e power j omega, gain versus frequency. You mark all the specifications, you will get 1 mark in the exam. Okay, now this is the step 1. Now what is my step 2? Step 2 is to calculate the order of the filter n. Now what is the formula for n? The order of the filter n is equal to log to the base 10 of 10 to the power of minus kp by 10 minus 1 divided by 10 to the power of minus ks by 10 minus 1 whole divided by 2 log to the base 10 of omega p star divided by omega s star. Okay, omega p it is. Okay, now we can simplify. We will get 1.97. So we can choose up to the next higher integer value. Okay, that is n is equal to 2. The order of the filter for the problem is 2. So therefore we will get 2 marks. So next, once you find the order of the filter, you can calculate the step 3 cutoff frequency. Step 3 to calculate the cutoff frequency omega c. Now what is omega c? Omega c1 plus omega c2 divided by 2. We can calculate that. So what is the value of omega c1? Omega c1 is equal to omega p star divided by 10 to the power of minus kp by 10 minus 1 whole raised to the power of 1 by 2 1. Similarly, what is omega c2? Omega s star divided by 10 to the power of minus ks by 10 minus 1 whole raised to the power of 1 by 2n. So you can calculate. So you will get 2 radian per second and you will get around 2.03 radian per second. So therefore what is omega c? 2 plus 2.03 by 2, you will get omega c as 2 radian per second. Omega c as 2 radian per second. So next step. Now next step 4, to find the transfer function hn of s. Now here n is equal to 2, therefore we can calculate h2 of s. Now what is my h2 of s? h2 of s is equal to 1 divided by product of left top poles of s minus sk. There are, for n is equal to 2, we will get 4 poles s0, s1, s2 and s3. Out of these 4 poles, s1 and s2 are left top poles and s0 and s3 are right top poles. Now consider the left top poles as from the previous discussions. So 1 divided by s minus s1 and s minus s2. And what is the formula for calculating sk? Sk is equal to, because of odd number, even number, 1 at an angle of pi k divided by n plus pi by 2n, and k is equal to 0, 1, 2, 3 dash dash till 2n minus 1. This is the formula. Now for n is equal to 2, after finding s1 and s2, we will come to know what is my h2 of s. h2 of s is equal to 1 divided by a square plus root 2s plus 1. Okay, this is h2 of s. Now from this we can calculate h of s. What is my h of s? h of s is equal to h2 of s, where s is replaced by s by omega c. So s divided by 2. You can substitute. You will get h of s is equal to 1 divided by s by 2 whole square plus root 2 into s by 2 plus 1. You can take the LCM. So you will simplify. You will get 4 will be the LCM. So 4 divided by s square plus 2 root 2 into s plus 1 plus 4. This is your h of s. This is the normal analog filter design for the given problem. Now we have to convert the last step. It is the last step. Now very very important, so carefully observe. Now we convert h of s to h of z. Now h of s is analog, now h of z is digital filter. So we have to use bilinear transformation. Okay, we have to use bilinear transformation. Now how to convert your h of s to h of z? So h of z is equal to h of s. Okay, where s is replaced by 2 by t into 1 minus z inverse by 1 plus z inverse. This is a transformation, and we know that default t is equal to 1 second. Now put this in the equation of h of z. So h of z is equal to h of s is 4 divided by s square. So s square is nothing but 2 into 1 minus z inverse whole square divided by 1 plus z inverse whole square. This I will take this as whole term as square. Okay, so therefore I will remove this particular portion, s square. So now plus 2 root 2 into s. So therefore 2 into 1 minus z inverse divided by 1 plus z inverse, okay, plus 4. Got it? Now what is simplification? You take the 1 plus z inverse whole square as an LCM. So now that 1 plus z inverse whole plus this is the LCM square, that goes to the numerator automatically. So we'll get 4 into 1 plus z inverse whole square is the LCM divided by, we'll get 2 square is 4. So 1 minus z inverse whole square divided by 1 plus z inverse whole square plus 2 square becomes 4, 4 root 2 into 1 minus z inverse divided by 1 plus z inverse plus 4. Now next step, h of z is equal to 4 into 1 plus z inverse whole square divided by 4 into 1 minus z raised to the power of minus 1 whole square plus 4 root 2 into 1 minus z inverse into 1 plus z inverse plus 4 into 1 plus z inverse whole square. Okay, so this will be in the form of a minus b into a plus b. Simplify. So this is a minus b whole square, this is a plus b whole square. Do the simplification. Okay, you will get h of z into, you can expand this, you will get 1 plus z raised to the power of minus 2 plus 2 z raised to the power of minus 1 divided by 0.586 z raised to the power of minus 2 plus 3.4142 is the final answer. This is the design, okay, in the digital filter for the given problem by using bilinear transformation. With this I will conclude today's class. Thank you.